If you are actively preparing for one of the most rigorous exams in our field, say, you're staring down the GCFA certification in advanced digital forensics, you realize pretty quickly that the scope of knowledge is just staggering.
It's immense, absolutely staggering.
You're expected to fluently navigate the deep technical details of the entire digital stack. I mean, one minute you're grappling with how Linux LVM metadata reconstructs a striped volume, and the next you have to recall the precise bit flags for encryption in an NTFS attribute.
It's a constant high-stakes balance, isn't it? Foundational hardware knowledge on one side, cutting-edge anti-forensics on the other. It really is the pinnacle of domain knowledge.
And that technical breadth is exactly why we wanted to structure this deep dive.
Right. Our mission today is to give you a comprehensive concepts refresher. We're drawing directly from the essential academic research and, the practitioner sources that really define this field.
We're going to try and distill those hard-won nuggets of knowledge.
The facts that separate that basic understanding from true, certified expertise.
We are going granular today. This is hyper-focused on the essential domains of a digital investigation. So foundational models, acquisition and preservation techniques, the complicated world of volume and partition analysis.
And then the deep dive into file system artifacts, FAT, NTFS, XCX, UFS.
And finally, of course, the crucial realm of memory forensics.
Understanding these layers is the key. We aren't just, listing facts here. We're exploring their forensic significance. Knowing the difference between the 3 timestamps a user sees versus the 4th hidden one in NTFS, for example.
That's the ball game right there.
It is. That's often the critical difference between building a successful timeline and having your entire case just collapse.
Exactly. And let's be honest, absorbing this massive volume of detail requires structured, efficient practice, especially under exam conditions.
Absolutely.
If you're tackling certification, you need a tool that forces that quick recall. And that's why, right from the start, we recommend something like Flash Genius. Tools like this, with their specialized AI-guided learning paths and domain practice modes, they're designed to make sure your study time focuses efficiently on the areas.
The really tricky parts.
Yeah, like remembering ATA commands or specific file system offsets. Where you need the most reinforcement, it's about being smart, not just putting in the hours.
Okay, so let's unpack this, starting at the highest level.
Yeah.
The methodology. Digital forensics is a mature discipline, but for years, the actual requirements for a legally defensible investigation were often neglected in the initial process models.
They really were.
Why did the field realize it needed to formalize its investigative requirements using these highly structured frameworks?
Well, it really stemmed from the need for professionalization and legal defensibility. I mean, as far back as 2004, researchers like Myers and Rogers were emphasizing the absolute necessity of standardization and rigorous certification.
Because it's not enough to just find the evidence. Not at all. When you present digital evidence in court, you have to prove not only what you found, but that your methodology was sound, repeatable, and adhered to strict standards. Traditional models often focused on the steps, collect, examine, analyze, but they failed to formally define the goals and anticipate the failures.
So we moved from just following a procedure to proactively modeling the entire investigative space. What methodology lets us formally model those goals and those anticipated failures?
We turned to formal requirements engineering, specifically the CHAOS methodology developed by Van Lansweerd. It stands for Kernel, Agents, Objects, and States.
Originally for software engineering, right?
That's right. But it maps perfectly to forensic requirements. It's a goal-driven methodology that systematically formalizes how the entire investigation processes, anti-forensics, personnel, systems, how it all relates to a specific objective.
Okay, so let's break down the core chaos concepts as they apply to forensics.
The central concept is the goal. These are the desired objectives, expectations, and constraints that must be satisfied for the investigation to succeed. A simple goal might be, all acquired evidence must be proven identical to the source data.
Simple but critical.
Absolutely. Then you have obstacles. An obstacle is just the negation of a goal. It defines precisely what could go wrong. So for that goal, an obstacle would be evidence integrity is compromised during transit.
Okay, so you're modeling the failure states.
Exactly. And the model also defines agents, the personnel responsible, like the forensic examiner in operations, which are the specific actions they take, like running a hash comparison.
I can see how mapping that out formally would be helpful, but I have to ask, in the heat of an incident, when practitioners are already relying on their SOPs, their standard operating procedures, does adding an abstract model like CHAOS truly reduce friction, or does it just add procedural overhead?
That is a fair and critical question. And the answer is, when it's executed correctly, the formalization offers profound benefits that go way beyond a simple checklist. We see, really, 4 dimensions of benefit.
Let's hear them.
First, procedural. It reduces the unnecessary data and management overhead because the scope is narrowly defined by the goals of the case, which prevents scope creep. Second, technical. These formal models allow the methodology to be modified quickly. A new OS comes out, new encryption. The model helps you identify which agents or operations need updating.
So it's adaptable.
Highly. Third is social. It helps capture the full attack capability, addressing both the technical and the non-technical dimensions of a crime. And finally, and maybe most importantly, legal. It allows for the clear, unambiguous expression of legal constraints. You're proving, in court, that every step you took was necessary to satisfy a legally defined goal.
So it turns an SOP into a verifiable, structured argument.
Precisely.
That makes the technical argument so much stronger. By formally defining the goal, ensure data integrity, the model inherently requires you to anticipate and mitigate the obstacles to that goal, which immediately forces the investigator to address anti-forensics.
Exactly. Anti-forensics is the ultimate obstacle. It's not just about destroying evidence. It's any situation that challenges the investigation process by contaminating any stage, its requirements, or actively destroying that evidence.
Things like data hiding, evidence destruction.
System contamination, obfuscation, all of it. A successful investigation must have models that anticipate these issues. If we know an attacker might use sophisticated self-deleting malware, our formal goal must include capturing volatile memory before that process has a chance to terminate.
We've seen several frameworks emerge to formalize the process. The hierarchical objectives-based one from Beebe and Clark and the event-based framework by Carrier and Spafford, they have different structures, but that initial foundational step, it remains constant across all of them.
Preservation.
Preservation.
It is the single most critical, non-negotiable step. The goal is straightforward. Reduce the risk of overwriting or modifying evidence. And to do that, we rely on the fundamental distinction between dead analysis and live analysis.
Tell us why dead analysis is always the preferred method, if it's operationally possible.
Because it's sterile. In a dead analysis, the system is completely powered down. That immediately terminates all active processes that could modify data. Once the system is off, we ensure that every single sector is copied, bit for bit, onto secure storage.
And crucially, you use a write blocker.
You must. We use hardware write blockers between the suspect drive and the collection system. A hardware write blocker is a device that physically intercepts any write commands from the acquisition system and ensures they never ever reach the original suspect media. It's the gold standard for preserving integrity.
But in incident response, especially in corporate environments, system uptime is often non-negotiable. Or, key evidence like active network connections or running malware processes. It will all vanish the moment you pull the plug.
Right, and that forces you into a live analysis.
And that is where the risk just skyrockets.
It really does. In a live analysis, the suspect operating system is running. If an attacker has compromised the kernel, maybe with a sophisticated rootkit, they can feed the acquisition tools false data. They can replace standard OS functions with their own malicious code, hiding their processes or modifying the data stream before it's even acquired.
So the system itself is lying to you?
It could be. And that's why, as a rule, live acquisition should be avoided unless the volatile data collected is strictly necessary. You just can't get it any other way. The results of a live acquisition will always face higher scrutiny in court.
Whether it's dead or live, integrity assurance is mandatory. How do we prove mathematically that the acquired image is an exact sector-by-sector duplicate of the original source media?
We use cryptographic hashing. Hash functions MD5, SHA-1, SHA-256. They generate a fixed size output, a unique signature based on the input data.
And the key property here is the avalanche effect.
It's exactly the avalanche effect and collision resistance. Even changing a single bit in the source data will dramatically alter the resulting hash value. It'll look completely different. So you calculate the hash of the source media before acquisition and the hash of the resulting image after acquisition.
If they match, you're good.
If they match, you have mathematically proven the integrity and non-alteration of the evidence. And that process is absolutely integral to the chain of custody.
This foundational understanding of models, preservation goals, and integrity assurance, it really underpins the entire field. Without this strict adherence, all the subsequent technical analysis is basically worthless in a legal context. If you're finding these frameworks and acronyms are blending together, that's a perfect area for some targeted review. Now we move down the stack to the metal, the absolute basics of digital storage. Before we even talk about acquisition tools, we have to address how the data is physically organized, starting with the smallest element.
The bit, the 0 or the 1. 8 bits make up 1 byte, and the byte is the standard smallest addressable unit of storage. It can represent 256 unique values, from 0 to 255.
And the moment we need to store any value larger than 255, like a timestamp, a large file size, a memory address, we move into multi-byte values and we run straight into the fundamental problem of endian ordering.
Yes, and this is an absolute necessity for manual hex analysis. It's the first hurdle.
So what is endianness?
Endianness just defines the order in which those multi-byte values are stored in memory or on disk. So let's take a 4-byte value, say the hex number 0 by 0, 1, 0, 2, 0, 3, 0, 4.
Okay.
In big endian ordering, which you see on older systems like SunSpark or Motorola PowerPC, the most significant byte, the 001, is stored first at the lowest memory address. The value is stored just like you would read it, 0, 0, 2, 0, 3, 0, 4.
But the vast majority of systems we analyze today, particularly modern PC architecture, use little endian.
Exactly. In little endian ordering, which is characteristic of IA32-based Intel systems and their descendants, the least significant byte, the 04, is stored first. So that same value, 0.010203034, is physically written to disk as 04030201.
It's completely backwards.
It is. And if you don't adjust your reading of hex dumps based on the system's endianness, you will misinterpret nearly every multi-byte structure, from offsets to timestamps. It leads to catastrophic analytical errors.
And along with order, we need to know the encoding of any strings we find.
Right. We're primarily dealing with ASCII and Unicode. ASCII is 1 byte per character, maxing out as 0 by 7E, which is fine for English text. But Unicode, especially UTF-16, uses 2 bytes per character, and you see it everywhere in modern operating systems.
Like in FAT's long file names.
Exactly. Or in Windows registry strings.
Mm.
You have to identify the encoding to translate those hex values back to meaningful text. And remember that strings are very often terminated by the NUL symbol, E0000.
Let's discuss the process of acquisition itself. There's a crucial rule of thumb regarding the layer at which we should be collecting data.
The primary rule is acquire data at the lowest layer possible where you expect to find evidence. For most cases, this means aiming for a disk-level acquisition.
So you're saving every single sector of the entire physical drive. Why is that so important?
Because a volume-level acquisition misses unpartitioned space, and a file-level acquisition, well, that misses deleted data, temporal data, and all the critical hidden structures within the file system metadata. You need the raw disk image for maximum evidence recovery.
Now, what happens when that low-level acquisition hits a problem, say physical damage? A scratch on the platter that results in a bad sector that just can't be read.
This is a specific test of a proper forensic acquisition tool. If a tool encounters a bad sector, the accepted forensic behavior is twofold. First, you log the address of the damaged sector for documentation. Second, you write zeros for the data that could not be read.
And why is writing zeros so important? Why not just skip that bad sector?
Because skipping the sector would result in an image of the wrong size. It would cause a shift in the linear block address, the LBA sequencing, for all subsequent sectors.
And that would throw everything off.
Everything. It breaks most subsequent analysis tools because they rely absolutely on the LBA integrity of the image. By writing a block of zeros, the image size and the LBA addressing remain perfectly intact, preserving the location of all the readable evidence.
That detail about LBA integrity is absolutely crucial. Okay, moving from accidental damage, let's talk about intentional hidden areas anti-forensics built right into the hardware layer, specifically the host protected area, or HPA.
Right. The HPA was introduced in the ATA4 specification. It's a configurable area, often at the very end of the disk, that hardware manufacturers use to store diagnostic tools or recovery environments. It makes them invisible to the standard operating system and formatting tools.
So how does an investigator confirm that a user or the OEM has hidden space in the HPA?
You have to compare the output of 2 specific ATA commands. First, you execute the read native max address command. That returns the true maximum physical address of the disket's total size.
The real size.
The real size. Then, you execute the standard identify device command, which returns the number of user-accessible sectors, the reported size. If the reported size is less than the true size, you know an HPA exists in that gap.
And to get to the data that's stored in there,
You have to use the set max address command, feeding it the true sector count you got from read native max address. This temporarily restores access to that hidden area. But it is absolutely vital to document this modification, because you are altering the disk's configuration.
You're changing the evidence.
Potentially, yes. So we often use a volatility bit setting. This ensures that the HPA status returns to its hidden state after the analysis system is powered off, which minimizes changes to the original evidence drive.
That sounds like a powerful hiding mechanism. But then the ATA6 specification introduced the device configuration overlay, or DCO, which is even more subtle.
The DCO is much stealthier. It can manipulate the hard disk's apparent capabilities and its size. A DCO can hide sectors even beyond what the HPA can hide, making the drive appear smaller even when you query it with read native MAC address.
So it caps the entire drive's reported size.
And its features at a lower level. It's very sneaky.
If read native MAC address is also lying to me, how do I find the DCO?
You have to execute the device configuration identify command. This command returns the actual features and size of the hard disk, bypassing the DCO's active limitation. You compare this output against the standard identify device and read native MAC address. If you see discrepancies, especially if the DCO identification reveals a greater capacity, you've confirmed a DCO is active.
So you have to check for both.
You have to. They're often used by sophisticated anti-forensic actors to hide entire partitions or volumes.
Moving to tools, we rely heavily on open source solutions. The Sleuth Kit, TSK, and its graphical counterpart, Autopsy, are really the backbone of many investigations.
TSK is the forensic toolkit, built for deep file system analysis. It provides command line tools for analyzing FAT, NTFS, X23, UFS, you name it. Tools within TSK like FLs can list files, including deleted ones, and Ls can list metadata like inodes or MFT entries.
And Autopsy puts a nice GUI on top of all that power.
Right. Autopsy provides that crucial graphical interface layered over TSK. It allows for timeline generation, keyword searching, hash database lookups. It just makes it much more practical for large-scale analysis.
And for the acquisition phase itself, we often see customized versions of the standard DD tool.
Yes, standard DD is problematic in forensics because if it hits an error, it just stops. Or if you use the wrong flag, it will skip data without logging it.
Which is a disaster.
It's a disaster. That's why we use tools like DCFLTD and its successor, DCSci. DCFLTD was designed to calculate the MD5 hash of the data during the acquisition and log errors gracefully. DCSci is even better because you can calculate multiple cryptographic hashes, MD5, SHA-1, and SHA-256 all in parallel.
So you get immediate integrity proof while accommodating stricter legal requirements. The granularity of knowledge here, from understanding how to read a hex dump to knowing the specific ATA commands for HPA and DCO detection, this is the level of detail required for advanced certification. If you're struggling to keep these highly technical specifications straight, that focused practice is essential for building that fast recall you need under pressure. We've established the physical layer and the bits. Now we have to address how the disk is logically organized into usable volumes, a step that's often fraught with confusion because of multiple layers of address abstraction.
Addressing is definitely complex because of that abstraction. There are three key addresses we always have to distinguish. First, the physical address. That's the linear block address, or LBA, starting at 0 on the very first sector of the disk.
Okay, that's the absolute start.
Right. Second, the logical volume address, disk. For the whole physical drive, this usually aligns with the LBA. But the third one is the most critical for file system analysis later on.
And that's the partition's logical address.
That's the logical volume address, partition. This address is relative to the start of the partition. So, for example, if the LBA of the physical disk starts at sector 0, but partition 1 is defined to start at LBA 5000, then the partition's logical address of LBA 5000 is actually 0.
So all your calculations inside that partition have to be offset by 5,000 sectors.
Precisely. If you are manually calculating offsets to find a file system structure like a superblock, you must use the partition's logical address, not the disk's physical address. Miscalculating that partition offset by just a few bytes will render the entire file system unreadable.
Moving to partition schemes, the old standard is the MBR, or DOS-based partitions. It's complex, really, because it was never designed for the scale of modern storage.
MBR is a legacy system through and through. It's limited to 4 primary entries in its partition table. To get around this, it introduced the concept of the extended partition.
Which isn't a volume itself.
Correct. The extended partition is a container that chains together multiple logical volumes, and the challenge for the investigator is following that chain. Each logical volume points to the next, forming a linked list. If that chain is broken or intentionally obfuscated, Reconstructing the logical layout becomes very, very difficult.
In other environments, particularly server systems, we find BSD partitions.
Yeah, BSD systems like FreeBSD or OpenBSD, they use a different structure called the disk label. This label holds a fixed-size partition table, often 8 or 16 partitions, and it's usually located in the second sector of the partition itself.
Which adds a layer of complexity.
It does, because you often find these BSD partitions existing within a single FreeBSD type entry in the legacy DOS partition table. It essentially requires 2 layers of partitioning analysis to locate the actual data.
Contrast that complexity with the modern standard GPT.
The GIAC partition table, or GPT, found on modern systems, especially those using UE5 firmware, is far simpler and more robust. It supports vastly larger disks and relies on globally unique identifiers guides for partition types. And, importantly, it stores redundant copies of the partition table at the beginning and the end of the disk.
So it's more resilient to corruption.
Much more. A big win for forensic reconstruction.
Okay, that covers single disk organization. But in large environments, we frequently encounter systems where multiple physical disks are combined into a single logical volume. This requires understanding RAID and disk spanning.
And when you're dealing with RAID redundant array of independent disks, the reconstruction headache can be massive. In Linux, RAID is managed by the multiple device, or MD, kernel driver. We frequently see level 0, which is striping for high performance but no redundancy.
Level 1, which is mirroring for full redundancy.
In level 5, striping with parity, which is a balance between efficiency and redundancy.
So how does an investigator find the RAID configuration to put it back together?
Well, the configuration can be stored in the OS config file at Crate tab, which is easy to find if the OS is intact. But in modern setups, the configuration is often written directly to the disk itself using a persistent superblock. It's marked as type 0axFD for DOS partitions.
Meaning you have to dig into the raw sectors.
You do. You have to examine the raw disk sectors to find the configuration metadata that tells you the stripe size, the RAID level, and the order of the disks.
And how is that different from disk spanning, like Linux Logical Volume Management, LVM, or Windows Logical Disk Manager, LDM?
It's a different goal. RAID combines disks to improve performance or redundancy, often interleaving data through striping. Disk spanning, on the other hand, simply merges storage space sequentially. Think of LVM. It presents disk 1 blocks 099, immediately followed by disk 2 blocks 099 as one giant volume. It's all about convenient storage expansion, not redundancy.
So if I have a set of Linux disks configured under LVM, what's the safest way to analyze that combined volume?
There's a structured procedure. First, you image all the component physical volumes. Then, in your trusted analysis environment, you use the LVM tools. You run VG-scan to locate the volume group metadata, and then VG-change AOY to activate the logical volumes.
And that makes it appear as a standard device.
Exactly. LVM then exposes the combined volume as a standard device in dev, like devmapper_my_volume. You can then image that as a single unit or analyze it directly as long as you maintain read-only access.
What about Windows LDM used for dynamic disks? That sounds much riskier.
LDM is notoriously complex and risky. Windows dynamic disks store LDM metadata across all the disks in the set. The primary risk is that if you import those LDM disks into an analysis system that also uses dynamic disks, the host OS might try to write new data to the LDM database to maintain its own environment.
Corrupting the evidence.
Instantly. While the Linux kernel does support LDM analysis, it often requires manual reconstruction, sometimes using the MD driver to manually assemble the volume maps rather than risking that native import process.
The need to differentiate between a physical LBA, a partition's logical address, and a complex volume assembly scheme like RAID 5 is the real test of expertise. If you can't accurately reconstruct the volume, you can't even begin to find the file system artifacts. We've established the address space. Now we move inside the most dense and critical area of forensics, file system analysis. This is where most of the evidence and the greatest challenges reside. Let's start with the generalized model that experts use to compare different file systems.
Right. We use a 5-part model to break down the function of any file system.
Yeah.
First, the file system structure itself, the layout, size, data, configuration, things like superblocks and boot sectors.
Okay, part 1 is the container.
Part 2 is the content, the actual file data stored in blocks or clusters. Part 3 is metadata, the descriptive data about the content, so your inodes in Linux or MFT entries in NTFS. Fourth is the file name layer, which links the human-readable name to the metadata address.
And fifth?
Fifth is application data. These are specific structures used by the OS or applications, like NTFS's log file or its change journals.
How the operating system chooses to allocate space is critical for deleted file recovery. Tell us about the different allocation strategies.
The strategy determines where the OS looks for free space. The first available strategy always starts searching for free clusters at the very beginning of the file system.
And the forensic consequence of that.
Is that deleted data at the beginning of the volume will be overwritten very quickly. So your best luck for recovery is often towards the end of the disk. Conversely, the next available strategy starts the search after the last allocated unit, which distributes new writes more evenly across the disk.
And best fit.
Best fit searches for consecutive blocks matching the needed size, which is primarily aimed at reducing file fragmentation.
And let's not forget the possibility of data hiding by exploiting the file system structure itself.
A subtle but effective technique, yeah. It involves exploiting the damaged sector flagging. File systems can mark data units as bad or damaged. While this was originally intended for hardware sparing, an anti-forensic actor can manually set these flags, store their hidden data in those units.
And the OS will just skip them.
Exactly. Most native OS consistency checks will then skip these marked units entirely. The investigator has to compare the acquisition tools report of actual bad sectors against the file system's internal list of marked units to spot that discrepancy.
Let's dive into the specifics, starting with FAT, File Allocation Table. Simple, pervasive, and often found on external media.
FAT is structurally simple. It uses a table, the FAT, to link clusters sequentially. It forms a chain that defines where the file's data is located. The key metadata, including the 8.3 short file name, or SFN, and attributes, are stored together in the directory entry.
But FAT supports long file names, LFNs. That significantly complicates the directory structure.
It does. LFNs are handled by requiring multiple additional directory entries that precede the standard 8.3 SFN entry. These LFN entries use a special attribute value, 0x0f, and here is a crucial point for manual analysis. They're stored in reverse order, preceding the SFN entry.
And they have checksum.
They do. To prevent corruption, each LFN entry contains a checksum that's calculated based on the SFN. This checksum is the only way to ensure the LFN fragments correctly correlate to the SFN.
And FAT deletion is simple, but often requires a manual step for recovery.
Very simple. When a file is deleted in FAT, the first byte of its directory entry is replaced with the hex value 0 by E5. The rest of the metadata remains intact, including the starting cluster number.
Which is why recovery tools often ask you to supply the missing first character.
Exactly. It's the only missing piece of data needed to fully restore the file path and metadata.
Let's talk about the timestamps, a critical forensic artifact that introduces international complication.
It does. FAT timestamps are stored with respect to the local time zone of the system where the write occurred. This is a massive complexity when you're dealing with evidence acquired internationally. You have to correctly ascertain the local time zone offset at the time of the write to convert it back to UTC for a unified timeline.
And the granularity varies.
It does. Created is optional, accurate to 1/10 of a second. Last accessed is optional, accurate only to the day. And last written is required, but only accurate to 2 seconds.
Now contrast that with the modern complexity of NTFS, New Technologies File System.
NTFS is a different world. It operates under the principle that everything files, directories, its own structures, is a file. The core structure is the master file table, or MFT. Every single file and directory on the volume has at least one entry in the MFT, which begins with the signature string file. The NFT is the central ledger of the entire file system.
Let's focus on the MFT's temporal data, specifically the 4 timestamps found in the standard information attribute. These are invaluable for building accurate timelines.
Yeah, so standard Windows properties show you 3 timestamps, but the MFT contains 4, and they're all stored in UTC, which simplifies international analysis compared to FAT. You have the standard creation time, modified time.
Which is when the content changed.
Right, and access time. But the 4th hidden value is the MFT modified time. This records the exact moment the file's metadata was altered. Maybe its name was changed or permissions were updated, even if the content itself wasn't touched.
That is a forensic goldmine. It often reveals malicious activity that's hidden from typical user-facing file property screens.
It really is.
NTFS uses B trees for indexing directory contents. How does this complex indexing affect deleted file analysis compared to FAT?
It makes tracing deleted files much harder. When a file is deleted, the MFT entry is marked as unused, but critically, Windows actively sorts and reallocates the index records in that B tree structure. This means the file name record of a deleted file may be quickly flushed from the index, making the recovery of the original path much more challenging than in simpler file systems.
NTFS is also engineered for advanced data handling, incorporating file compression and sparse files, which complicates data recovery.
All right, sparse files are files that contain large sections of zero data. NTFS only allocates physical data units for the non-zero data, saving space. The forensic challenge is distinguishing between data that was genuinely never written and data that was written as zeros.
And compressed attributes.
With compressed attributes, the file system compresses data into units or chunks. If the compression is efficient, it creates sparse runs, and the investigator has to analyze the data attribute to understand the compression status and reconstruct the original data stream.
And the ultimate layer of data hiding in NTFS is encryption, EFS.
EFS is highly complex. The content is encrypted symmetrically with an algorithm like Deus Ex and a unique file encryption key, or FEK. But the FEK is then encrypted using the user's public key. That's asymmetric encryption. Decryption requires the user's private key, which is itself stored in the registry, encrypted with the user's login password.
It's a nested nightmare.
It is. But we've noted a key vulnerability or forensic opportunity with EFS.
Yes, tell us about that.
Despite the robust encryption, the design flaw is that when a file is initially encrypted, a temporary plaintext copy is often created. And it might temporarily exist in an unwiped temporary file called efs0.tmp or be written to the swap space or page file.
So you can sometimes find the original plaintext in unallocated space.
Exactly. Sophisticated recovery techniques focus on recovering that temporary plaintext copy before it's overwritten.
Finally, before we transition to Linux, NTFS uses two critical logging systems, log file and the change journal.
The log file is the file system journal. It records transactions using logical sequence numbers, LSNs, for crash recovery, but it's too low-level to be easily interpreted by a human investigator. The change journal, or extensus GIAC, is far more useful. It records specific changes to files and directories using update sequence numbers, USNs.
But it's not always on by default.
Correct. But if it is enabled, it provides an invaluable chronological record of file modifications, creations, and deletions that applications use to track recent activity.
The structural differences between FAT and NTFS are enormous. This is a primary area where candidates need rigorous domain practice, focusing on which artifact exists where. Again, perfect for targeted tools to lock down those details. Now let's transition to Linux environments and the XTX family, XT2, XT3, XT4.
Right, XTX file systems are organized into distinct block groups, and they use enodes for metadata management. The enode acts similarly to an MFT entry, but it points to the data blocks. The superblock is the configuration heart of the file system, located 1,024 bytes from the start, and it contains critical configuration details, with backup copies distributed across the block groups for redundancy.
X-3 introduced journaling for faster recovery, but it adds a wrinkle for the investigator analyzing the raw disk.
It introduces an oddity in endianness. While most XTX data structures conform to the little endian ordering of the Intel architecture they typically run on, the XT3 journal data is written in big endian ordering.
So it's flipped.
It's flipped. An investigator has to remember this exception when manually parsing the journal entries, or they will completely misinterpret the sequence numbers and timestamps within the journal stream.
What specific deletion clue does XTX leave behind that is highly useful for event reconstruction?
XTX offers a subtle but powerful artifact. When a file is deleted, the inode is marked as unallocated, but the directory entry structure is manipulated. Specifically, the record length of the previous directory entry is incremented to span and skip over the deleted entry.
So it's like a pointer just jumps over the deleted file's entry.
Exactly. And by analyzing this linkage manipulation, an investigator can sometimes reconstruct the order in which multiple files were deleted from that directory, providing a crucial clue for mapping out a sequence of malicious actions.
Finally, we examine UFS, Unix file system UFS1, UFS2, often found in BSD environments in Solaris.
UFS uses cylinder groups, which is a similar concept to XTX's block groups. UFS inodes are central to file location, and they use a complex system of pointers to locate data blocks. Direct, single indirect, double indirect, and triple indirect pointers.
And the number of indirect pointers determines the max file size.
Correct. And UFS2 supports dynamic inodes, adapting their size based on the file system's needs.
Are there any unique challenges or opportunities regarding deletion in UFS?
Yes, and it depends on the specific flavor of Unix. In DSD systems, when a file is deleted, the directory entries are easily located, and crucially, the inode value associated with the deleted file is not cleared.
That's helpful.
Very. It means the investigator can perform a quick check. If the deleted file's inode number is not currently allocated to a live file, the associated data blocks might still be recoverable. But if you were analyzing a Solaris system, the inode value is cleared, which removes that quick recovery test.
The comparative forensic knowledge required for certification is immense. Moving from NTFS's reliance on 4 UTC timestamps to FAT's local timestamps, or understanding how Linux directory entries provide deletion order clues that Windows NTFS obscures. This is the heart of deep file system expertise. We have thoroughly explored non-volatile evidence. Now we move to the most ephemeral, time-sensitive evidence, volatile data captured through memory forensics. This is indispensable for incident response.
The guiding principle of memory forensics is often quoted: malware can hide, but it must run. Analyzing running processes, open handles, network connections, the state of the OS kernel. It's often the only way to find modern fileless malware or malicious activity that resides only in RAM.
And the industry standard tool here is volatility.
Without a doubt.
So tell us about a typical volatility use case in a live incident response.
Volatility is essential for rapidly creating a map of a compromised system. A key module is NetScan, which enumerates all active and recently closed network connections. For example, volatility can identify a suspicious process, maybe one disguised as a common system service like refresher..Exe,
Right.
making persistent connections to an unknown public IP address over non-standard ports like 443 and 8080. If that activity matches known indicators of compromise for a command and control server, it allows security teams to instantly isolate that machine and pivot to check other devices for the same signature.
Volatility has undergone significant evolution. What was the most important functional change in the latest major version, Volatility 3?
Volatility 3 dramatically streamlined the analysis process.
Right.
Previously, to analyze a RAM dump, an investigator had to manually identify the precise OS, the architecture 32 or 64-bit, and even the service pack of the source machine.
Which was often a huge pain.
It was time-consuming and sometimes impossible. Volatility 3 introduced a unified profile system that eliminates the need for manual profile specification. It significantly accelerates the triage and analysis phase, allowing practitioners to focus on the evidence content rather than the system metadata.
Let's pull back and look at the broader context of forensic science. It seems that investigation methods are evolving across disciplines, extending beyond purely digital systems. Why is it important for the digital forensics expert to pay attention to these adjacent fields?
Because the challenges are universal. We're seeing advanced imaging technologies like virtual autopsy, multi-detector computed tomography, or MDCT, and AI-driven image analysis being integrated into forensic medicine. These non-invasive techniques offer immense precision and can be culturally sensitive alternatives to traditional autopsy.
And the interesting parallel is that these emerging fields face the exact same foundational hurdles that digital forensics battled when it was setting up frameworks like KA.
Precisely. They struggle with high operational and financial costs. MDCT scanners are incredibly expensive. They face ethical and legal considerations regarding data security and the potential for algorithmic bias in AI-driven analysis. And most critically, they lack standardized protocols.
So it's the same fight all over again.
It is. Just as digital forensics needed to define what constituted valid evidence collection, forensic medicine needs to standardize how AI models interpret and report findings across international borders.
So the battle for standardization and legal admissibility isn't unique to us. It's a universal problem every data-intensive forensic discipline has to solve.
Absolutely. The lessons learned in digital forensics, the necessity of formal modeling, the strict adherence to integrity assurance, the clear separation of goals and obstacles are all transferable. The potential for cross-cultural and international forensic collaboration through AI-enabled imaging is vast, but it hinges on solving those same issues of standardization and integrity that we spent the past decades solving in the digital realm.
So digital forensics is now influencing how other older forensic sciences manage the influx of new, complex data.
It really is. So today we've traversed the entire digital forensic stack. From the philosophical, the goal-driven necessity of formal investigation models like KAS, all the way down to the micro details of data storage.
Knowing how to interpret hex based on big versus little endian.
And the anti-forensic traps hidden in hardware geometry like HPA and DCO.
We then dove deep into the logical structure of evidence, understanding volume management via RAID and LDM reconstruction, and the core artifacts of the 4 major file systems. We covered FIT's local timestamps, NTFS's 4 temporal values, including that critical MFT modified time.
And the unique deletion clues found in XTX and UFS.
And finally, we addressed the capture of immediate evidence via volatility.
And remember, success in advanced certification hinges not just on recognizing these complex concepts, but on instant, quick recall and the ability to apply them under pressure.
And that requires intentional, rigorous practice that goes beyond simple textbook reading. If you're targeting a certification, make sure you are practicing with tools designed to replicate exam conditions. Flash Genius, for instance, offers real exam simulations designed to mirror those timed, high-stakes conditions, ensuring that when you walk into that testing center, you're confident, your recall is fast, and you are not surprised by the format or the difficulty.
We'll leave you with one provocative thought to mull over. Given that file systems are engineered to become increasingly complex and opaque, NTFS introducing active encryption, extensive journaling, sparse compression, cloud environments moving data far from local control, how will forensic practitioners continue to maintain standardization and consistently prove the integrity of evidence when the underlying data structures are designed to be actively self-modifying or purposefully difficult to read without specific proprietary keys?
So the challenge of integrity assurance just grows exponentially with every advance in system complexity and security.
It does. It's a constant